Okay, this is recapping Conjectures and Counterexamples, Lesson 3-1. We did this on the 3rd or the 4th on October 3rd, 10-3. Best way to get into it is to get into it. We want to make conjectures from data. The owner of an ice cream shop collected data on the total sales of the first 5 months that the shop was open. We want to make a conjecture about the sales total in the 6th month and explain some reasoning. So the first thing to do is look for some patterns. We're looking to see some patterns and draw some conclusions. From the 1st, 2nd month, we see things increased by 200. Then we see things increased by 250. Then things increased by 300. Then we see things increased by 350. Based on the pattern we see here of 200, 250, 300, 350, you might think that the next number we'd add is 400, which means 1,600 plus 400 gives us 2,000 in the 6th month. That's going to be our conjecture. We saw a pattern. We were looking for a pattern in our numbers. We found a pattern, and we applied it. We're making the conjecture. The sales of the shop will be $2,000 in the 6th month. The sale of the shop will be $2,000 in the 6th month. Our reasoning behind it is we see a pattern. We see the sales are increasing, and their sales are, the increase in sales is increasing, or the sales increase is increasing. The increase in sales, the increase in sales is increasing $50 each month. Now, we see the pattern of 200 plus 250 plus 300 plus 350. And so we're making the guess that we'll be adding 400 next month. We're going to be adding $400 in sales. We're going to have $2,000 in sales total. But do we know for a fact that we'll have $2,000 in that 6th month? We don't. Do we know for a fact that we'll have $400 increase in sales that month? We do not. What we have to recognize is that we're just looking at a pattern. We're looking at data. So it's a prediction. It's a best guess. A conjecture is truly an educated guess. Based on a pattern. If you can identify a pattern and extend it, then rule that you're making for that pattern is the conjecture, and it's making you, and anything you predict from it is also conjecture. We're going to make a conjecture, a prediction, about the shaded quadrilateral that describes the pattern in the sequence. So here we see it shaded, and we see it here, and we see it here. It seems that the shaded quadrilateral is moving. Now in class, you guys said a handful of things. Somebody said the shaded quadrilateral skips a step. So starting here, skip one, and here, and here. And then starting here, skip one and here, skip one and here. We also said two things. We said the picture rotates, or the quadrilateral rotates. And some we were able to identify how much it rotates. From here to here, the picture is rotating 90 degrees. We said clockwise. Now, some of you also said we were rotating the other way. We could have been rotating around the other way. We just said the picture rotates 270 degrees counterclockwise. And we did a quick sketch of it. Any of these conjectures could be correct because they all describe the pattern we see. The next step in our sequence, though, we predicted would be a picture like this here. Now, examples 1 and 2, we had some data, we had some pictures. We could see the pattern, we could look for a pattern visually. Sometimes you have to make patterns, or you have to make some data, or pictures, to actually then see the pattern. That's what example 3 is about. We want to make a conjecture about the sum of the squares of two consecutive natural numbers. We're going to list or draw some examples to support our conjecture. So to start off with, let's identify some examples. We want to sum up, add the squares of two consecutive numbers. So let's list two consecutive numbers, 1 and 2. Let's square them and add them up. 1 squared plus 2 squared, that's just 5. Well, let's look at another one, because one number is not a pattern. We could do 2 squared plus 3 squared. That's 4 plus 9, that's 13. We could do 3 squared plus 4 squared. 9 plus 16, that's 25. We could keep writing down pairs of numbers that are consecutive, one after the other, squaring them, and adding them together. We could do 4 squared plus 5 squared. 25 plus 16 is 41. 5 squared plus 6 squared. 25 plus 36 is 61. We could do 6 squared plus 7 squared. 36 plus 49. 85. 85. And we could say, do we see a pattern in our numbers? The pattern never has to be complex. We just care about our answer. So we got a 5, a 41, a 13, a 61, a 25, and 85. If there's something relating all of these numbers, well, the thing that we can make a comment on is all the numbers are odd. So our conjecture, since we see that pattern, our conjecture is going to be the phrase, the sum. It's going to be this phrase that we're concerned about, the sum of the squares of two consecutive natural numbers. The sum of the squares of two consecutive natural numbers is odd. It's a mouthful, but it's our conjecture. It's what we can see from our pattern. Last thing we wanted to take a look at were counterexamples. We don't know that our conjecture is true. It's a guess. It's an educated guess. While it looks like it could be true, we could do this for hundreds and thousands of millions of pairs of numbers. To show it's true for all cases, we have to actually prove it. And it's only going to take one example to show conjecture is not always true. If we can find that example, we call it a counterexample. That counterexample could be something as simple as a number, a drawing, or a statement to show things are not true. To find a counterexample, we're going to find a counterexample to show each of these conjectures is false. If n is a real number, then minus n is a negative number. Well, I don't have any numbers or examples yet, so we might as well try things out. Let's try out 5. Plenty of people suggested 5 in class. If n is 5, 5 is a real number. What's that say? Well, that says that negative n equals negative 5. Is negative 5 a negative number? Yes, that is true. Which means this is an example, but not a counterexample. We tried out a number. We found that when we used that number, we got a statement that matched this. That doesn't work for us. We want to find a real number that, when we change its sign, becomes not a negative number. So then some of you realized we could try a different number. We could try n equals negative 5. If we chose that number, if we chose n to be negative 5 is a real number, then negative n gave us a positive 5. And that works for us, because is 5 a negative number? No. So this would be an example of a counterexample. We found a number, negative 5, that is a real number, but when made negative, when changing the sign, it becomes a positive number. We found that the first part of our statement was true, and the second part of our statement was false. Last was, if angle ABC is congruent to angle DBE, then angle ABC and angle DBE are vertical angles. We want angles that are congruent, and they're saying if the angles are congruent, then they are guaranteed vertical angles. A counterexample is just saying we want angles that are congruent, but not vertical angles. We want the counterexample. We'll write that out. Should look like angles are congruent, but not vertical angles. And, well, I had you guys try out some pictures, and you eventually settled on one. You found you could draw a picture like this. You have an angle A, B, C, and an angle D, B, E. These two angles are not vertical angles because I don't have straight lines. Remember, vertical angles need straight lines. You need two intersecting straight lines. But here I've at least marked them as congruent, and that meets the requirement. Angles are congruent, but not vertical. This picture would be the counterexample. with this page, you had 8 problems on the back that we went over on Friday. You should have taken pictures of the front page and the back and submitted them under Lesson 3-1, Conjectures. The assignment you want to match this with is Lesson 3-1, Conjectures. There's a counterexample assignment that is IXL 2GJ.